For this section, you have to understand about inverse functions and what they are and how you can find them given an original function. So I'm just going to show you quickly with a function you're familiar with, which is y equals x squared. So this is a rough graph of y equals x squared here. Now we're going to find out as we go, to make sure that you end up with an inverse function, your original function needs to be one-to-one. Now from methods, you'll probably know this is not a one-to-one function. Okay, but I'm going to work with it anyway just to see what happens. So to find the inverse, what we need to do is look at our original function, which is y equals x squared. It's also here written f of x equals x squared, so f is a function of x. We need to swap x and y in our original function. So what I'm going to do is where there was a y, I'm going to write an x, and where there's an x, I'm going to write a y. Okay. The next thing I have to do is solve this equation for y. So what I'm going to do here is take the square root of each side, and remember that you need to do plus or minus the square root so I can get y on its own. So I've solved for y. Now this function here is what we call the inverse, and the way we write that is we put a little -1 up with the f equals, and then we put down what we've found. Now the little -1 does not mean 1 over f of x. That's not what that means. Okay, it's just a little label that tells us it's the inverse. Okay. The other thing that we want to do as well when we're finding inverses is to remember that the domain and range for the original function that we looked at will also swap. So for our original function here, we know that our domain is all real values for x, because it can be anything to the left or the right, and our range for y, as long as y is greater than or equal to 0, that works. Okay, so everything up. So what that means for our inverse is our domain and our range are actually swapped. The reason for that is when you swap x and y, you swap x and y in the domain and range as well. So the domain now is going to be x greater than or equal to 0, and the range is going to be y is anything that is a real. Okay. Now to sketch this, plus or minus square root, what that looks like, and I'll do this in a different colour. This is going to be our inverse function here. We'll sketch. So the plus square root, this is actually the plus square root part of the graph, and this part under here is the minus square root. So now we've sketched it, we need to check that our inverse actually is a function. Okay, there are two types of things that you can graph, relations and functions. Not every relation is a function, so we have to be very careful. To make sure that we have a function, what you should be able to do is something called the vertical line test. So you should be able to take a vertical line, and as it says here, draw vertical lines through the graph, and it should only cut through the graph once. If it cuts through more than once, it's not a function. And you can see here that if I take vertical lines and actually cut, you can see we're cutting through more than once, except on the end here where we cut through once. So this is actually not a function, and the reason for that is what we started with is not one-to-one, and we can check this by using horizontal lines. Okay, this is actually not a one-to-one function. We've got for every x value here, let's say x equals 0, or let's say x equals 2 and -2, we've actually got the same y value that happens for both of those values. Okay, so this is actually not a one-to-one graph. So what we're going to do to make sure that what we end up with our inverse is actually a function, we're going to do something called restricting the domain. Okay, so I'll do that on the next page. So we're going to use the same graph again. This time let's restrict the domain to make the function one-to-one. What that means is for every x value you should have one y value. And the simplest way to restrict the domain for y equals x squared would be to keep just half of the graph, because now you can see you've got one x value and one y value that corresponds. You don't have the other side anymore. Okay, so this is still my original function, which is x squared, but this time I've restricted the domain. So the domain is now x between 0 and infinity. Oops, round bracket. And the range is still the same, so still going from 0 up to infinity. Like that. Okay, so what we're going to do now that we've got a one-to-one graph, we're going to sketch our inverse again. Now we know for our inverse that we need to swap the x and the y, and we ended up with y equals plus or minus the square root of x. Now we have to think about our domain here, our domain and our range. Let's swap them again. So our new domain is going to be x between 0 and infinity. And because they're both the same, it won't make any difference really, which is which. So this is telling us we're only dealing with positive values. What that means is for our inverse, we actually don't have both sides anymore of that square root. We're only going to have the positive square root. So when we graph this now, and I'll do this in blue, our inverse function, so we know that our inverse function is now just the square root of x as opposed to x squared, so it's the opposite. That's this part here, like that. Okay, that's the sketch. And we know this is a function because if we drew vertical lines through, we'd only cut through that graph once. Okay, so this is the true inverse function for this function, provided it has a restricted domain. So often you'll need to restrict the domain for your function before you find the inverse. The last thing I'll show you just quickly is if you're sketching graphs and their inverses, and I'll just put this on a new axis. With this one in particular, we've got our original function here. So 1 and 2, 1 and 2. I just want to make it a little bit more exact. 2 goes to 4, like that. Excuse me, do it like that. Okay, so that's our original function, x squared. When you're actually sketching these, if you sketch the inverse function and the original function on the same set of axes, what you'll find is if you draw a line, and I'm drawing this line through y equals x, this acts as a kind of mirror line for your graph. So the original function, which in this case was x squared, is mirrored over this line to find the inverse. I'll do the inverse in green. And the interesting thing is too, there's actually 2 points of intersection with this mirror line at 0, 0 and at the point 1, 1. So when we draw our inverse, we flip this over the line here. It stays attached where it's intersecting, but everywhere else it's going to flip. It's going to look like that, roughly like that. We'll do that again. So this is our inverse function. So the relationship between a function and its inverse is that they are reflected over the line y equals x. And the reason for that is y equals x is a very special type of function. The reason f of x equals x, so that's y equals x. If we try and find the inverse of that, remember we can swap x and y, guess what happens? The inverse, swap x and y, well, you know what? It stays exactly the same. So this is the only function where the original function and the inverse are actually equal to each other, and that's y equals x. There's no other function that does that. So that's why that's our mirror line there. All those points will stay on the line y equals x. Any other points on a graph will be flipped over to the other side of that line. So inverses, swap x and y, solve for y, change your domain and range, swap them over, and if you're sketching both of the graphs on the same axes, you can simply reflect over the mirror line y equals x.